Howdy! Welcome to Elementary Statistics. I am Lance Curtis, and this is a lecture for Section 7.1, Estimating a Population Proportion. Here in this first lecture for Chapter 7, we're going to start by talking about the point estimate for proportions, and then we'll segue into talking about confidence intervals, confidence levels, and how to interpret them properly. We'll then go and talk about critical values, which we've already discussed in Chapter 6, but we're going to apply them to confidence intervals here in Chapter 7. Introduce a concept called the margin of error, and then we'll get into confidence intervals that are specifically made for proportions, and then round up the lecture talking about sample size. So, in this first section, we're going to present methods for using a sample proportion in order to estimate the value of a population proportion. This is one of the purposes of inferential statistics, which is to take characteristics of a sample and use those characteristics to make inferences and conclusions about a population. In this way, we don't have to know everything about every member of a population. We simply take what we need from the sample and then use that to estimate what we want to know about the population. Now, as we learned in Chapter 6, proportions are unbiased estimators. So that means the sample proportion is the best point estimate of the population proportion. We can then use the sample proportion to construct a confidence interval that estimates the true value of the population proportion. And so, knowing how to construct those confidence intervals and knowing how to interpret them is really important. We're also going to find out how to calculate the sample size that we need in order to make that estimate of our population proportion. So to start with, let's talk about population point estimates. In general, a point estimate is simply a single value or point on a number line that's used to approximate a population parameter. Since proportions are what we call unbiased estimators, the sample proportion p hat is then the best point estimate of the population proportion p. For example, the Pew Research Center once conducted a survey of 1,007 adults, in which they found that 85% of them know what Twitter is. In this case, the best point estimate of P, the population proportion, is the sample proportion P hat. So the sample proportion P hat is 85%. That's what we found from the survey, and we would then go and extend that to the population and say that we estimate the population proportion to be around 0.85. But there's some error involved with that, and we're going to get into that error later in this lecture. First, we need to understand the concept of a confidence interval. So confidence interval, otherwise known as an interval estimate, is simply a range or interval of values used to estimate the true value of a population parameter. So the point estimate provides the center for this interval, and then extending out either way to the left and the right on a number line, so to speak, from this point estimate is a margin of error. Those together comprise a confidence interval. Confidence intervals, as I mentioned previously, are sometimes called interval estimates because we're saying that an estimate of a population parameter is located within this interval that has a lower limit and an upper limit. Sometimes CI is used to abbreviate confidence interval, and you're going to see me using this abbreviation quite a bit. So if I ever say CI, you know I'm talking about confidence interval. A confidence level, as opposed to a confidence interval, is the probability, 1 minus alpha, that the confidence interval actually does contain the population parameter. So we construct an interval to estimate our population parameter, and then we associate with that interval a certain level of confidence. For example, we could say we're 95% confident that the true population parameter is located within this confidence interval. The confidence level can be however we want, and it's equivalent to 1 minus alpha, where alpha is basically the area in the tail of your distribution outside the confidence level. So the central portion of the distribution, that area under the curve, is going to be our confidence level, and then alpha will correspond to the area in the tails outside that central area. This is where critical values, which we've already seen in Chapter 6, come into play. We'll get into that a little bit more detail later on. For now, let's focus on confidence level. The definition that we've given for confidence level assumes that the estimation process is repeated a large number of times. That's assumed with the way that we're defining confidence level. The degree of confidence and confidence coefficient are simply other names for confidence level. So if you hear any of these terms, understand that they are interchangeable. The most common choices for confidence level are 90%, which corresponds with an alpha level of 10%, 95%, which corresponds with an alpha level of 5%, and 99%, which corresponds with an alpha level of 1%. There's a lot of ways to interpret confidence intervals, and many of them are incorrect. So let's focus on how do we interpret a confidence interval correctly. To illustrate this, suppose we have the proportion confidence interval 0.828 to 0.872 based on a sample size of 1,007. What this means is that we're 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion P. Another way to look at this would be to say, suppose we selected many different samples of size 1007. So we have multiple samples of the same size, and that size is 1007. And we're going to construct corresponding confidence intervals for each of those samples. If we did this, 95% of those intervals would actually contain the true value of the population proportion P. That's an alternative way to think about this. Personally, I like the first way to think about it. It's pretty simple and straightforward, and it's easy to remember. And so I'm all about simple, seeing how lazy I am. So yeah, that's going to be the way that I'm going to think about it. If that doesn't work for you and the second way to look at it works for you, that's fine. They're both saying the same thing. It's just looking at it from different vantage points. We can use confidence intervals informally to compare different data sets. The thing that you have to be careful, though, is never to use overlapping confidence intervals to make formal and final conclusions about the equality of proportions. In a way, that's kind of like saying, well, I'm comparing apples and oranges, and yeah, they're both fruit, but that's kind of where the comparison ends. From that, they tend to diverge in their characteristics pretty radically. So, yeah, you want to be careful when you're making an overlap of confidence intervals, making conclusions from that overlap, because realistically, the parameter from the population that we're estimating could be anywhere within that interval. So it might be within the region of overlap between two different intervals, but it might not. So that's where you get into trouble with making formal and final conclusions from an overlap of confidence intervals. So yeah, you can look at them and make some informal comparisons, but you can't go too deep into the interpretation, because that true value of your population parameter could be anywhere. It could be in the region of overlap, could be outside the region of overlap. We simply don't know. I mentioned earlier we were going to talk about critical values, so let's get into that now. we can actually use z-scores, which are called critical values, to distinguish sample statistics that are likely to occur from those that are unlikely to occur. So as I mentioned previously, the confidence level is going to be that area underneath our distribution curve that's centralized, and the area in the tails is going to be equal to alpha. So alpha and the confidence level are complements of each other. The z-score separating each tail region is commonly called z alpha over 2. So when you see z alpha over 2, what that means is that our critical region is comprised of both tails. That's why it's z alpha over 2, because half of the area for alpha is in one side of the distribution and the other half is on the other side of the distribution. If you see z sub alpha without being divided by 2, then typically you're looking at an area in the tail that's on the right side of the distribution. And you're not looking at a two-tailed feature, you're looking at a one-tailed feature. Z alpha over 2 in this case is the critical value because it separates z-scores from sample proportions that are likely to occur, which are those within the confidence level area in the center of the distribution, from those that are unlikely to occur, those that are in the tails of the distribution. Here we have a table where we're showing again critical z-scores that correspond to different confidence levels. So a confidence level of 90% corresponds with an alpha of 10%, or 0.1. If you put this into the standard normal distribution calculator or look at a z-score table, you'll find that this corresponds with a critical value of 1.645 because you have 5% on either side of the distribution. Likewise, with a confidence level of 95%, that corresponds with an alpha level of 5% or 0.05, and that gives you a critical value of 1.96. 99% confidence level leads to a critical value of 2.575. Now, I've mentioned previously, that these values are good to memorize because they keep coming up over and over again. But most people don't have to make a conscious effort to memorize them. You just work enough problems to where you see them often enough to where you know, okay, 90% confidence level is equivalent to a critical value of 1.645. You just tend to know it by experience. Notice there are two critical values for a two-tailed region. We have a positive z-score on the right and a negative z-score on the left. Both of these critical values are needed to describe the total area alpha underneath the curve. Let's look at an example of how to find a one-tailed critical value. So in this instance, we have z sub alpha. So this is indicating we have the entire alpha area, and usually that area is going to be on the right side of the distribution. So our confidence area is on the left, and the z-score, the critical value, is separating that confidence interval area from the alpha area on the right. So if we're given a confidence level of 75%, that means the area under the curve that corresponds with 75% is on the left. So in our normal calculator inside StatCrunch, we're going to take the default settings for mean and standard deviation because we want the standard normal distribution to calculate a z-score. We then put less than or equal to for our inequality sign dropdown because we're given the area for the confidence level. That corresponds to an area to the left. So we want less than or equal to, and then put the area in on the right side of the equal sign for your probability calculation. That's the area that corresponds with the confidence level, which is 75%, and then hit compute, and out comes your z-score, your critical value, z sub alpha, 0.67. Let's look at another example. But before that, we need to remember that the confidence level is the area under the curve outside the critical tailed region. So the tail region, which corresponds with alpha, is going to be on the right. Now, if I wanted to, I could have solved this problem by saying, okay, I'm going to change my inequality to wanting to look at greater than or equal to, so I'm getting the area on the right, but then I'd have to put in 0.25, 25% for my area. I'd get the same number that comes out. So however you want to think about it is fine. Just remember that your critical area alpha is the tail region on the right, and the confidence level area is on the left. So this in effect means that 0.67 is our critical value, z sub 0.25. Remember, alpha is the area in the tail, so z sub 0.25. Let's look at another example. Let's say we have a confidence level of 84%. So we're going to put those values into our normal calculator in StatCrunch. So 84% is our area. We want the area to the left because that corresponds with the confidence level. And then that gives us our z-score of 0.99. This then is our critical value. So 0.99 is equal to z sub 0.16. 0.16 being the complement of 84%. For a two-tailed critical value, we've got half the area on the left and half on the right. This is not a problem in StatCrunch because we can just use the between option, which allows us to calculate our critical z-score values. Now, what allows us to do this is the fact that the area for alpha is split directly in half. So we're balanced on the left and the right as far as the area underneath the curve. This is what allows us to use that between option in StatCrunch. So for a confidence level of 75%, we simply put our values in, and out comes our two critical values. Notice one is negative and one is positive. So when you're answering questions on homework assignments, for example, you need to include both the positive and the negative values, because it's both of these values that define the region in the tails. It's not just one, it's both of them. This is a two-tailed critical value. Again, remember that your confidence level is the area under the curve outside the critical tailed regions. Since in this instance we have two-tailed critical values, the region we're looking for is in the middle of the distribution in between the two tails. Let's again look at another example of 84%. So in our normal calculator, we're going to select the between option and then click on 84%. This gives us our two critical values, negative 1.41 and 1.41. Both of those values together are the critical value. So it's not just 1.41, it's the positive value and the negative value together that comprise your two-tailed critical values. This brings us to the concept of margin of error. So once we have the critical values are synonymous to the margin of error in a confidence limit. We can estimate a population proportion with data from simple random sampling, and the margin of error is in the maximum likely difference between the observed proportion p hat and the true value of the population proportion p. In other words, the margin of error is defining the lower and upper limits of our confidence interval. This margin of error is denoted by a capital letter E. Notice that we've used the capital letter E before for a concept known as expected value. Here where we're dealing with confidence intervals, E does not mean expected value. E means margin of error. We calculate it with this expression here. So we're going to take our critical Z value and then multiply it by the square root of the product of the population proportion multiplied by the complement of the population proportion divided by the sample size. So the probability of getting the margin of error is going to be 1 minus alpha. This is the same as our level of confidence that the interval we're constructing contains the true population parameter, in this case, the population proportion. Now, you might also hear the margin of error referred to as the maximum error of the estimate. These two expressions are synonymous. I'm not that familiar with maximum error of the estimate in the sense that I haven't encountered it that often in my stint in industry. So I'm just going to talk about margin of error. But if you do hear maximum error of the estimate, understand that you're talking about the same thing. Let's look closer at our margin of error equation to understand each of the different parts so we know what it is that we're dealing with when we calculate this value. E, of course, is the margin of error. Z sub alpha over 2 is the critical value, the z-score that separates likely and unlikely values. P hat is our sample proportion. Q hat is the complement of the sample proportion, and N is the sample size. So we need each of these values located on the right in order to calculate margin of error on the left. Constructing confidence intervals for proportions, the method that we use has certain assumptions associated with it. So first of all, we're assuming the sample is a simple random sample. We're also assuming that the conditions for the binomial distribution are satisfied. This assumption comes from the fact that we're taking p hat and multiplying it by q hat, the complement of p hat. So we need to make sure there's a fixed number of trials, the trials are independent, there are two categories of outcomes, and the probabilities remain constant for each trial. We need to know that there are at least 5 successes and 5 failures. So right there off the bat, any sample size less than 10 is not going to satisfy these assumptions. We can also express confidence intervals in different ways. So this is simply a different format for writing a confidence interval. The most common is what you see here, where we've got our point estimate in the middle, separated out by a lower limit and an upper limit, from which are just created by subtracting and adding the margin of error from or to the point estimate, respectively. We can also look at it as an ordered pair, where we list the lower limit and the upper limit inside parentheses and separated by a comma. We could also list it as the point estimate plus or minus the margin of error. Each of these formats is basically giving you the same confidence interval, just in a different way. And of course, different circles have different conventions about which format they prefer. So it's good to know how to convert between one format and another. However you format your confidence interval, there is a convention to round the limits of your confidence interval to 3 significant digits. Let's look at some examples for exchanging from one format to another. So here we have one format, and we're asked to convert into another. The format we're given is that 2.5 is less than p hat, which is less than 0.75, and we need to convert this into the form p hat plus or minus e. To do this, we need to find out the value of p hat and the value of e. The simplest way to conceive of this is to think about your limits of your confidence interval as being points on a number line. Your point estimate p hat is directly in the middle between these two limits, the upper limit and the lower limit. Because it's directly in the middle between the upper limit and the lower limit, we can average those two numbers to find out the value of p hat. In this example, when we do that, we get 0.5. So 0.5 is the value directly in the middle between 0.75 and 0.25. This is our p hat. Now we just need to find our margin of error. The margin of error is the distance from p hat out to either one of its limits. So we have the distance to the upper limit, the distance to the lower limit. They're going to be the same because p hat is directly in the middle between those limits. So if we simply take the range from our limits and divide it in half, that gives us the value for e, in this case 0.25. So then we can rewrite our confidence interval as 0.500 plus or minus 0.250, again using the convention of 3 decimal places for each of the values in our confidence interval. Let's look at another example, 0.412 to 0.908. So here the numbers aren't so nice, but the process that we just got done describing and going through is going to work regardless of what these numbers are for our limits. So first, let's imagine our limits as numbers on a number line. Our p hat value is going to be directly in the middle between those two values. To find the value directly in the middle, we're going to average our limits together. So when we do that, we get 0.660. This then is the value of p hat. Our margin of error is the distance from our point estimate out to either the upper limit or the lower limit. And we can find this value by taking the range, which is the maximum minus the minimum, or the upper limit minus the lower limit, and then dividing by 2. This gives us 0.248. With these two numbers, we can then rewrite our confidence interval in a different format, 0.660 plus or minus 0.248. Let's go over a process that we're going to go through repeatedly for constructing these confidence intervals. First, you want to verify that the required assumptions are satisfied. Remember that our method of construction, of conforming these confidence intervals, depends upon certain assumptions being satisfied. So make sure they're satisfied first. The sample must be a simple random sample, and the conditions for the binomial distribution must be met. We also need to have at least 5 failures and at least 5 successes. This allows us to use the normal distribution to approximate the distribution of sample proportions. The second step is to find the critical value z-score that corresponds to the desired confidence level. We then calculate the margin of error. We find the values for our upper and lower limits and place them in the general format for the confidence interval. And we then round resulting limits to 3 significant digits. Let's look at an example in which we illustrate this construction method. We looked earlier at this Pew Research Center poll, which surveyed 1,007 randomly selected adults and reported that 85% of respondents know what Twitter is. From this statement, we know that our sample size is 1,007. We also know that the point estimate, our sample proportion p hat, is 85%, or 0.85. By deduction, the complement of p hat, which is q hat, is then 0.15. We just take 0.85 and subtract it from 1. That gives us the complement, which is 0.15. So with those values identified, we're now asked to answer the following questions. First, what is the margin of error E that corresponds to a 95% confidence level? 2, what is the 95% confidence interval estimate of the population proportion P? 3, based on these results, can we safely conclude that more than 75% of adults know what Twitter is? And 4, how can we briefly but accurately describe the results and include all the relevant information? Let's look at each of these questions one at a time. First up, what is the margin of error E that corresponds to a 95% confidence level? First, let's check to make sure our assumptions are satisfied. Do we have simple random sampling? This is the part where you say something. So if you're not saying something, answer the question, do we have simple random sampling? Yes, we do have simple random sampling. Do we have a fixed number of trials? Yes, we have a sample size of 1,007. So there are a fixed number of trials. Each trial being, we're asking each person in that sample size the same question. Do you know what Twitter is? Are the trials independent? Yes, they are independent. The answer one person gives is not going to influence the answer any other person gives. Assuming that, we're not taking all 1,007 people and putting them in the same room and asking them all at once. But generally, that's the way these surveys go. They're actually conducted on an individual level. So yes, we could say the trials are independent. Are there only 2 outcomes per trial? In other words, with each person that you ask the question, are there only 2 outcomes? The answer is yes. Either you know what Twitter is or you don't. So the answer is yes or no. You know what it is or you don't know what it is. So there's only 2 possible outcomes in each trial. Is the probability of success constant with each trial? Yes, the probability of success is constant with each trial. There's a certain proportion that knows what it is. And while we're conducting the survey, that proportion is not changing. So yes, the probability of success is constant with each trial. Do we have at least 5 successes and 5 failures each? The answer is yes. With a sample size of 1,007 and a success rate of 85%, it's a pretty sure thing that we have this requirement met. The only way that this requirement would not be met is if our success rate were either so low that we didn't have 5 successes or so high that we didn't have 5 failures. That's not the case here, so we have this requirement met. And this was the last of our requirements, so it appears that all of our assumptions are satisfied. We can go ahead and use our methodology, which is to use the margin of error equation that we looked at earlier. So here's the equation. We plug in what we know, so a 95% confidence level is going to correspond with a critical value of 1.96. We put in a value for p hat, which is our proportion of success. That's 85%. The complement of that is 15%. Sample size 1,007. Punch that out on your calculator, and you should get 0.0221. This then is our margin of error. Notice that I'm actually taking this out to 4 decimal places. I'm doing that because at the end we're going to round to 3 decimal places, so I want at least 1 extra decimal place in there to help me avoid potential rounding errors. Because the second question is going to ask us to calculate a 95% confidence interval estimate of the population proportion P. So first we need to find our point estimate for the population proportion. The point estimate is going to come from our sample proportion. Because the key question, does the sample proportion target the population proportion? The answer to that is going to be yes, it is going to target because proportion is an unbiased estimator. So that means we can just take the sample proportion and use that as our point estimate for the population proportion. So P equals P hat, which we know from the problem statement is 0.85. Now we substitute the given values into the desired general format. Typically, when you're asked to solve a problem, there's a format that will be specified, so we need to pay attention to that. I'm just going to use this standard format because it's the one that I've seen most frequently used out in industry. So here we have p hat minus e on one side for the lower limit, p hat plus e on the other side for the upper limit, and in the middle we have the point estimate p. Plug in the numbers that we know. So p hat is 0.85, our margin of error, which we calculated for the previous question, 0.0221. Punch it out in your calculator and you get 0.828 to 0.872. This then is our 95% confidence interval estimate of the population proportion. Notice how we rounded our limits to 3 significant figures. This is a standard convention regardless of which format you use for the confidence interval. Next question. Based on these results, can we safely conclude more than 75% of adults know what Twitter is? Well, let's ask the question a different way. Is the true population proportion greater than 75%? That's essentially what this question is asking. If more than 75% of adults know what Twitter is, then the true population proportion should be greater than 75%. Let's look first at our 95% CI, our confidence interval. 0.828 to 0.872. This says that we're 95% confident that the true population proportion is located somewhere between 0.828 and 0.872. All these values are greater than 0.75. So yes, it is safe to conclude more than 75% of adults know what Twitter is. It may help for you if you can't conceptualize it in your head with what I've just described. It may help for you to think of confidence intervals in terms of a number line. So here's a number line with the upper and lower limits for our confidence interval. The true population proportion is located somewhere in between those values. The question we're asked is, can we safely conclude more than 75% of adults know what Twitter is? Well, 75% is located out here on the left. Notice how the entirety of our confidence interval is located above 0.75. So therefore, we can conclude safely that yes, we are 95% confident that yes, the true population proportion is greater than 75%, which means more than 75% of adults do know what Twitter is. Let's look at our last question we were asked. How can we briefly but accurately describe the results and include all the relevant information? Well, there's many possible ways to answer this question. Let me just give you a couple. First, we could say 85% of adults know what Twitter is. That percentage is based on a Pew Research Center poll of 1,007 randomly selected adults. In theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points in either direction from the percentage that would be found by interviewing all adults in the United States. Another way to answer the question would be to say this. According to a Pew Research Center poll of 1,007 randomly selected adults, 85% of adults know what Twitter is. The 95% confidence interval margin of error for that statistic is 2.2 percentage points. Between these two examples, I actually like the second one better because it's shorter. It's much more brief, succinct, to the point. It communicates all the necessary information, and it does so in a very brief and concise way. Whatever way you use to describe the results, there are two pieces of information that you need to make sure you communicate. The first is the confidence level, and the second is the sample size. Think for a moment about the reports you've heard in the media from the results of surveys. How many of them actually cite the confidence level for the intervals that they are describing? I mean, almost all of the reports that I've seen in the media for surveys don't even touch the confidence level. There are a few that mention the sample size, but there's also quite a few that don't mention the sample size at all. They simply say there was a survey conducted. So it's really important that you communicate each of these pieces of information because it lets us know vital parts of the statistical results and the analysis that was actually done to achieve those results. Now, when you're looking at poll results, you want to consider that the quality of the results you get depends greatly on the sampling method you use. We saw that earlier when we were looking at chapters 2 and 3, and the population and the sample size. So how many people you're actually sampling. The more people you sample, the more data you have, and the more reliable your inferences are going to be. The size of the total population that you're sampling is usually not a factor in the quality of the results that you get. So just because the sample that you take is a small percentage of the population, don't think that the results you're getting are unreliable. As long as you've got the minimum requirements for sample size met, you're good to go. We're going to be talking here in a moment about those requirements for how do we calculate that minimum sample size. First, let's look at another problem to illustrate how we're conducting a confidence interval. So an online company wanting to know if customers would be interested in purchasing a new flavor combination conducted a poll on their website in which 73% of 23,854 visitors said they would be interested in trying it. What is the 95% confidence interval estimate of the population proportion? Well, first we're going to get our point estimate, p hat, which is 0.73. This is the 73% who said they would be interested in trying it. The complement of that is going to be q hat, which is 0.27. We simply take the 0.73 and subtract from 1. Our critical value z-score is 1.96 because we're looking for a 95% confidence interval. We can actually get that number out of StatCrunch by using the normal calculator or going to a z-score table to get the same value. Remember to use the between option when you use the calculator in StatCrunch because we have z alpha over 2. So therefore there are 2 critical values that we need to form our critical area. We have all that we need now to calculate our margin of error. So we go to our equation, substitute in the values that we know, and then punch it out in our calculator, which gives us 0.0056. Now I can go into a standard format for confidence intervals and substitute in my values for the point estimate and margin of error. Calculate this out, and we get 0.7244 to 0.7356, which, rounded using the convention of 3 decimal places, will then be 0.724 to 0.736. This is our confidence interval, 95% confidence interval, I should say, estimate of the population proportion. Now, does the confidence interval that we've calculated provide a good estimate of the population proportion? You have 4 answers here. I'll give you a moment to read them over and make your decision. So in answering this question, does the confidence interval provide a good estimate of the population proportion? We really need to ask ourselves first, what exactly does make a good estimate of the population proportion? What variables or factors do we need to pay attention to in order to make a good estimate of the population proportion? And we talked about those on the previous slide. The first one that we need to consider is sample size. And the second that we need to consider is the sampling method that we're actually using. So these two items together form the factors that are most important for providing a good estimate. So what factors of these did we use to make the actual confidence interval? Well, the sampling method that we used was an online poll. What type of sampling method does an online poll correspond to? Well, I hope you said voluntary response, because that's what that is. And we know voluntary response samples typically are not characteristic of the populations from which they are derived. And so here, the correct answer is going to be C. No, the sample is a voluntary sample and might not be representative of the population. We can't really do anything with the sample size. We do know what the sample size is. It's 23,854, but we don't yet know how to calculate what the minimum sample size is. I can tell you, though, that for most things you'll look at in the real world, if you have a sample size of almost 24,000, you're very much good to go. Okay, so a sample size is not a factor, but the sampling method is, and so that leads us to the correct answer for our question. Let's talk about this issue of sample size. I mean, how big does a sample have to be in order to estimate the population proportion? Let's go ahead and learn how to calculate that. So the way we're going to do this is we're going to take our margin of error equation and solve for sample size. Because if you remember, the margin of error equation that we have includes sample size as one of the variables we need to know in order to calculate margin of error. So what we're going to do is we're going to take this equation and now we're going to solve it for sample size so that we can get an equation that lets us calculate the minimum sample size that we need. So the first thing I'm going to do is divide both sides of my equation by the critical value z-score, z sub alpha over 2. That brings that value over to the left side of my equation. Then what I'm going to do is I'm going to take the reciprocal of both sides. So I'm basically flipping my fractions over on each other. So what was on top goes on the bottom. What was on the bottom is now on the top. To get rid of my radical sign, I'm going to square both sides of my equation. This then removes the square root sign from the right side. And then I get to multiply both sides by p hat q hat. That brings those elements over from the right side of my equation to the left side of my equation. And now I have n isolated all by itself, but I like to have those variables that I isolate on the left side. So I'm just going to flip everything around, and that gives me the final equation for calculating the minimum sample size that I need to estimate a population proportion. N equals p hat q hat times the square of my critical value z-score divided by the square of my margin of error. Now, there are instances in the real world and in some of your problems on your homework assignment when an estimate for p hat will not be known. In those instances, we can simply substitute 0.25 for p hat q hat. That then gives us this equation for estimating the minimum sample size that we need to estimate the population proportion. No matter which of these equations you use, when you get done with your calculation, you want to round up to the next largest whole number. What we're looking for is a discrete value because we're having to count individual items. And so a partial item doesn't do us any good. So you want to round up to the next largest whole number. Let's take a quiz and see if we can remember what we just learned about sample size. So for each example below, find the minimum sample size required, the estimate, the population proportion or percentage. So with a margin of error of 0.2, 90% confidence level, and p hat of 0.75, they give us p hat right off the bat. That's our point estimate, 0.75. We then know that q hat is 0.25 because it's the complement of p hat. So just take the 0.75, subtract from 1, and that gives us our q hat. We know our critical value z-score is 1.645 because we can calculate it from StatCrunch, or we can simply look it up in a table, or we can simply have done so many of these problems that we know what that value is. Our margin of error is 0.02. This was given to us in the problem statement. And so now we have everything that we need to calculate our sample size. So we substitute those values that we have into our equation, punch this out on our calculator, and we get 1268.45. Of course, we're going to round up to the next nearest whole number, so that gives us 1,269. This then is our minimum sample size in order to construct a confidence interval of 90%. Now, let's say we have the same values that we did before, only this time we don't know what p hat is, which means we're not going to know what q hat is either. In this instance, we can simply substitute 0.25 for the product of p hat, q hat. Our z-score hasn't changed because our confidence level is the same. Again, if you want to run through the calculation again, you're free to do so. It's going to come out the same. Then we want the same margin of error because that number didn't change. So we take the equation that we have for calculating minimum sample size, and we plug in our values. Notice that p hat q hat is replaced with 0.25. The other values are the same as they were before. When we punch these numbers into our calculator, out comes 1691.27. So then we round up to the next nearest whole number, and we have a sample size of 1,692. Notice the difference made in the minimum sample size required based on whether we know what the sample proportion is or we don't know what the sample proportion is. Not knowing your sample proportion adds an extra 400 people or units or whatever it is that you're sampling. You've got 400 more of them to put into your sample size before you can get the same level of confidence your interval is going to contain your true population parameter. So it makes a big difference to know what that little piece of information is. Let's look at an example to illustrate this concept of sample size. There are many companies that are interested in knowing the percentage of adults who buy clothing online. This is especially true if you're in the market of selling clothing. How many adults must be surveyed in order to be 95% confident that the sample percentage is an error by no more than 3 percentage points? So let's take the information from this problem statement and use it to calculate our sample size. We can answer by using a recent U.S. Bureau statistic that 66% of adults buy clothing online. Or we could simply answer without any prior knowledge of the possible value of the proportion. Let's look at each one of these examples to show you how the calculation is done. So first, we're going to use the Census Bureau statistic that 66% of adults buy clothing online. This is going to be the first of our variables that we identify from our problem statement. P hat is 66% or 0.66 because this is what was stated there in the problem statement. 66% of adults buy clothing online. This then means that Q hat is going to be 0.34. We simply take the 0.66, subtract from 1, that gives us Q hat 0.34. Our alpha level is going to be equal to 1 minus the confidence level. The confidence level is 95% because in the problem statement it says that we want to be 95% confident. So that means our alpha is 0.05. That then leads us to a z-score critical value of 1.96. And of course, margin of error 0.03 because in the statement it says 3 percentage points. That's the equivalent of saying 3%, which is 0.03. Now that we've got the numbers that we need, we substitute into our sample size equation and solve. So here's our sample size equation. We're going to plug in the numbers that we have. So 0.66 for p hat, 0.34 for q hat, 1.96 for our z-score critical value, and 0.03 for e. Punch these numbers out on your calculator, and you will find the answer is 957.84, which of course we round up to the next nearest whole number, and we get 958 for our sample size. So, to be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 958 adults. Let's solve the same problem, only this time we're not going to have that Census Bureau statistic. In fact, we're not going to know anything about what the proportion of our population is going to be that actually buys clothing online. So we're going to go through the same process, identify the variables from the problem statement. We don't know what p hat is, so what do? Well, that means we don't know what q hat is either. In this instance, what we can do is substitute 0.25 in and use it as an estimate for p hat q hat. We then go and get the other values we need to calculate our sample size. So our alpha value is the complement of our confidence level, 95%, and that means that our alpha is going to be 5%, which leads us to a critical value z-score of 1.96, and we know that our margin of error is 0.03 because, again, 3 percentage points is in the problem statement. Next, we substitute these values into our sample size equation and solve. Here's our equation. Substitute the values in, punch this out on your calculator, and you'll get 1067.11, which we round up to the next nearest whole number, 1068. So, in order to be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1068 adults. Notice again, not knowing that sample proportion really ups the ante on that minimum sample size that you need in order to have the same confidence level. Let's look at another example involving the heights of presidents of the United States. So in the data file for presidents of the United States that we have in our StatCrunch group, we find that 47.4% of the 38 U.S. presidents in the file were taller than their electoral opponent. If we consider the data in our file to be a sample of the whole, which is not that far-fetched because we've had more than 38 presidents since our nation was founded, what is the 95% confidence interval estimate for the population proportion of U.S. presidents who are taller than their electoral opponents? Well, the first thing we want to do is get that p hat value, which we get from our problem statement, 47.4%, or 0.474. That means that q hat, or the proportion of presidents who are not taller than their electoral opponents, is 0.526. We can calculate a critical value z-score of 1.96 from the fact that we want a 95% confidence interval estimate. Again, we can go into StatCrunch to get that if need be, but if you run through enough of these problems, you'll already know that's the value you need. Now we have everything we need to calculate our margin of error, so we plug in the values that we know, 1.96 for our critical value z-score, 0.474 for p hat, 0.526 for q hat, 38 is our sample size. Punch this out on our calculator, and out comes 0.081. We then have everything we need to calculate our confidence interval. So using the general form that you see here, we substitute in the values that we have, 0.474 for p hat, 0.081 for margin of error, and out comes 0.393 to 0.55. This then is our 95% confidence interval estimate for the population proportions of U.S. presidents who are taller than their electoral opponents. Does it appear from this information that greater height is an advantage for presidential candidates? Well, I'll give you a moment to look at your confidence interval and decide what you think the answer will be. Well, here I hope you're looking that if height were actually an advantage, then taller candidates should win elections more than half the time. Because, I mean, you win more than half the time, that means that there's something there that gives you an advantage. Well, the CI that we calculated is mostly underneath 50%. So, no, it doesn't appear that height gives us any advantage. Now, there is that small portion there on the right side where, yeah, the true population proportion could be slightly higher than 50%, but given that each value within that interval has an equal likelihood of being the true population proportion, and there's much more possibilities of being less than 50% than there is being more than 50%, so it's safe to conclude that height doesn't appear to give any notable advantage. That brings us to the end of this lecture. If you have any questions, you know what you need to do. Otherwise, I will see you in the next video or in class. Thanks for watching.